is a pretty, there was a request made for me to turn my camera on, so I'm going to do that. I don't know why anybody would request to look at me, but here we go. So there's a lot to cover under electricity and wiring, so we're just going to jump right in. I do want to go ahead and mention that if there's any pro partners on this webinar today, if you're planning on being in Las Vegas next week for the Pro Partner Conference, please come up, find me. If you see me, come up and introduce yourself. I'd love to meet you if we haven't already met. I know I know a few contractors that are going to be there, but anyway. So with any electrical repairs, anytime you're doing anything with the electrical system, right? We want to use best practices, and we want to be safe, right? You want to make sure that everything is grounded properly. We're talking about grounding a little bit. You want to make sure that the power is off to the unit before you start messing with it. Never assume that any electrical device is properly grounded. Don't walk up to a condensing unit, and I'm terrible about doing this. Don't walk up to a condensing unit and just put your hand or your arm on it and lean over it without making sure that it's grounded properly. It's very possible that if you have a short to ground or a dead short and there's not a good ground, that cabinet could be energized and you could get shocked or electrocuted. So we always want to be safe. Remember, electricity will kill you. Just don't be afraid of it. Just give it the respect that it deserves. So we're going to start out with some electrical theory. If you've been to any of my classes before, I'm a big fan of sort of understanding why things work the way that they work. And I think once we all have a good foundation of how electricity works, it makes it a lot easier to troubleshoot, or at least it does for me. So essentially, we're going to start with atomic theory, right? And what that is that all matter, everything in the universe is made of atoms. And those atoms are constructed out of a nucleus, which has protons and neutrons. And then around that nucleus orbits electrons. Just like the solar system, just like a planet and its moons, it works the same way, right? So you've got in the center, you've got your nucleus that is positively charged. And then around that, orbiting around that nucleus, you've got electrons, and those electrons are negatively charged. And some electrons have an unstable outer ring. And really what that means is that you have an odd number of electrons. So if you look in the middle graphic, this is a copper atom. And so the outer ring of this copper atom has a single electron, and that is referred to as a free electron. And what happens in with free electrons is, well, they're considered conductors, and we know that copper is a great conductor. Atoms that have a stable outer ring, so if this copper atom were to have two electrons in the outer ring, well, it wouldn't be copper anymore, but it would be an insulator, and that outer ring would be stable. And so the way electricity flows and the way electrons flow is that free electron can be pushed from one atom to the next atom. So when we move that free electron from the top atom, it bumps the free electron from the middle atom down to the atom below it. And it's that push that's called electromotive force that starts those atoms, that starts those electrons moving from atom to atom to atom. And as those electrons are moving down that chain of atoms, that is our electrical flow, right? So that's our current or our voltage. And we can do that in a couple of different ways. We can do it chemically with a battery, and then we can do it magnetically with an alternator, a generator, or a transformer. And that's how we get That's how we get that flow of electrons. It's called electromotive force or electrical potential. And that's where our electricity comes from. So there's three aspects of electricity or electrical flow that we need to talk about and discuss and maybe define. And the first one is voltage. And voltage is really just that electromotive force. And there's two different types. There's alternating current or volts AC. And in that alternating current, we have got our electrons bounce back and forth, right? So they go from our positive, negative, all the way through to the negative, and then all the way back. So we got positive and negative bouncing back and forth. And in the US, we use 50 hertz, and that's 60 times per second. So anything that has any sort of electrical current or voltage going to it, is that current is alternating back and forth 60 times a second. So when you think like a light bulb or a motor or anything else, that voltage that is powering that is actually flipping off and on 60 times a second. It's happened so fast that we can't see it. But if you have a very high speed camera, and depending on what type of filament or what type of light bulb you have, you can see the bulb maybe glow a little bit brighter and maybe get a little bit dimmer multiple times over a second. The same thing will happen if you point a video camera at a TV screen. You'll see that flicker. That's because they're not synced up. The hertz aren't synced. And then there's direct current, which is volts DC. Typically that happens with a battery, and that is just going one way. So our current is not bouncing back and forth. It's just going in one direction. Most of, I don't know that we're really going to go into DC current much today. We're going to talk mostly about AC. So that's voltage. So current is measured in amps or amperes. And when we're measuring current, right, you have your multimeter, and we'll look at a multimeter here in just a second, and the jaws on your multimeter, when you clamp them around any conductor, right, any wire, what you're measuring is the magnetic field that gets created as current or voltage is flowing through. So as those electrons are moving through that conductor, it creates a magnetic field, and the intensity of that magnetic field is what we call amps or current. So when you clamp your meter on, you're measuring the intensity of that magnetic field that's created around that current. 1 amp is the current required to flow through a resistance of 1 ohm with a pressure of 1 volt. And I'll show you a graphic here in a second that'll maybe put all that together. Which brings us to resistance. So resistance is measured in ohms, and really that is how difficult, that's a measurement of how difficult it is to move those electrons through that conductor. An ohm is a resistance that will allow 1 amp to flow with a pressure of 1 volt. And there's a mathematical formula that if you have any two, you can find the third. So here's the graphic that I was talking about. It's sort of an old graphic, but I think it helps to illustrate exactly what's happening, right? So our volt or our electromotive force or our electrical potential is the push that makes the electrons flow through the conductor. The amp is the actual measurement of the electrons flowing in a circuit. And then the ohm, as you can see, is the rope sort of tightening down the tube that we're moving through, or the conductor, is the resistance to that electron flow. So the higher the resistance, the harder it is for those electrons to move. The harder it is for the electrons to move, the higher the amperage has to be. So this is, and this is not a math class, but this is some calculations of Ohm's law, right? So Ohm's law is named after George Ohm, who was a German physicist who sort of discovered that that current is equal to electromotive force divided by resistance. So E is electromotive force, or volts. I would be current, and that's French for intensity de courant, current or amperage. And a lot of times those terms are interchangeable, right? Current and amps, resistance and ohms. Rarely will you hear somebody ask you to measure the electromotive force with your meter. They always say volts. But current is amperage. That's the same thing. Resistance is measured in ohms. So in any two of these that you have, you can calculate the third. So an electrical circuit. So an electrical circuit is the path that electrons flow. And in any circuit, you got to have three things. You have to have a power source. In this example, we got 120 volts AC. You have to have a control, and that is our switch. And sometimes your control really could be a super manual type control where you just unplug it, right? That you shouldn't. You should always have a control, but just the act of plugging that outlet in is sort of a control in and of itself. And then you have to have an electrical load, and that would be your bulb. When the switch is on or closed, it completes the circuit. Some people refer to having a closed switch as a made switch. Whether it's closed or made, that switch is completing the circuit so the electrons can flow out of the outlet, through the switch, through the light bulb, which is our load, and then back. If the switch is off, it is open, or the circuit is broken. The same way that we have an electrical circuit on an outdoor unit, a condensing unit, right? Our power source is the panel or the disconnect. Our switch is going to be the contactor inside our condensing unit. And then our load, or the light bulb in this case, is going to be the compressor and or fan motor or whatever else is in this outdoor unit, right? What other line voltage components are in this unit.
Wait, somebody's asking if there's a formula for how many ohms are required to prevent a short.
Formula, how many ohms are required? I don't know. So I'm not an electrical engineer. I've never had that question. We will talk about volt amp readings with transformers in a little bit, and that might sort of be along the lines of what you're asking. Let's get through that, and if that doesn't answer your question, maybe I'll ask a follow-up and I'll have to get back to it. So electrical circuits, we have got a couple of different types of circuits, right? So we have a series circuit, which is a single path that our electrons take, right? So you can see here we have got our power source, which is our L1 in neutral, so that's a 120 volt circuit. We've got a closed switch, and then we've got a motor. Motor is running, switch is closed. We've got electrons running through that motor. In the second diagram, we have got another motor added. So this is a parallel, or these motors are wired in parallel, meaning that each motor is wired to the same source, but they're not sharing the same voltage. And in this example, our switch is open, right? So at the top of our switch, or actually at the very end of our switch connection here, the end of our throw on our switch, our voltage or our electromotive force or our electrical potential is just sitting right there waiting for us to close the switch so that it can keep on moving through the circuit. And then we could have a series parallel, which is a combination. You can see that in the bottom diagram, we have got, we've added switches to each one of our loads, right? So we've got the ability to independently control each one of these motors. So that is a series parallel, or they're wired in combination. So we got really three types of diagrams when we're talking about electrical wiring, and these will be located in the installation manual. They'll be in PTS under wiring diagrams, and they'll also be on the panel somewhere, right? So on an outdoor unit, you pull off the electrical panel, flip it over. Sometimes you'll have a wiring diagram there. There's typically one on the indoor product. Sometimes those diagrams can get damaged, but you can always get them online on PTS or in the installation manual. So the first one we're going to talk about is a schematic. Schematic is also referred to as a ladder diagram. And in that ladder diagram, it shows and identifies the components, and it really sort of illustrates how the unit works, the electrical connections, and how all of the components work together. A pictorial diagram shows more of the locations of the components, and it lists the color of the wire. And then we have a factual diagram, which is really a pictorial diagram and a schematic diagram that are right next to one another. You can do your troubleshooting with one or the other, but it's a lot easier if you can look at both. And we're going to go through some examples of that here in just a second. Both of these diagrams are shown de-energized, right? So meaning that whatever control we have is open or broken. So this is a schematic from an RA14. And you can see over on the left-hand side, we've got the component codes. So that's a list of all the abbreviations of the components that are on this diagram. You can see our incoming voltage or our line voltage is L1 to L3. And then on both sides of that, between L1 and T1 and L3 and T3 is our contactor. So you can see in this example, we've got a open set of contacts between L3 and T3 and a closed set of contacts between L1 and T1. So L1 and L3 would be considered our line voltage side because it is the power coming in before our control. And then T1 and T3 would be the load voltage side because it's the voltage coming out of our control. So line voltage, load voltage. Well, we've also got some controls, right? And you can see here we've got a crankcase heater control that's CHC. And then down at the bottom, we have got a low ambient control. These controls are both line voltage, right? So they're 240 volts controls. And each one of them has a symbol. If you look back up at the CHC, it's got sort of this little squiggly line. And that lets me know that it is a temperature control. And then at the top of that is our switch. And because the sort of the red line now is touching both sides of that switch or both contacts on that switch, we can see that it is a normally closed switch. The low ambient control is a pressure control, and that little the semicircle with the the line coming out of the top of it indicates pressure, right? So on the crankcase heater control, that squiggly line indicates temperature. On the low ambient, that sort of semicircle indicates pressure. And you can see also that this is a normally closed switch. So by looking at this diagram, I can see that these switches are supposed to be closed. So when I start doing my troubleshooting, if I check across either one of these switches and they're open, then that lets me know that I have a problem. So as we sort of expand out or back out of our schematic control, not only do we have the line voltage or the 240 volt side of it, but we also have the control voltage or the low voltage side. Right? And so we've got our contactor, right? CC is our compressor contactor. But then on the bottom, we've got the contactor connections for our low voltage. And when we look at the pictorial diagram, you'll see that the contactor is just one piece instead of being broken up by voltages, by high voltage or line voltage or control voltage. And then down at the bottom there, 4 and 5, we have got our Y and our common, right? Y would be cooling from indoor, and then the brown or Y or yellow, and then the brown wire would be our common. Onto our pictorial diagram. So we were just talking about the compressor contactor. There's a red box around the contactor now, and you can see that in this pictorial diagram, we mix both the line voltage and the control voltage. So that's just the difference between a schematic or a ladder and a pictorial diagram. You can see coming out of T3, we have got a red wire going to the run terminal of our compressor. We have got a black going to common, and then we have got an orange wire also coming out of T1 going to the common terminal on our capacitor. Then possibly, right, so this dotted line lets you know that that is an optional wire or some things that you might not see in every unit, right, depending on model number and features. And then that black wire is going to wire into some other, if it's there, right, some other optional components, right? Let me go back, sorry. Like a crankcase heater, crankcase heater control, high pressure control, hot gas, and then low ambient control, which would all be listed on the component code over on the left, whether that is in that unit or not. So then on to the factual diagram, which is, like I said, a combination of both diagrams. We have got the schematic or the ladder diagram over here on the right. Then we have got the pictorial over here on the left. And between looking at both of these diagrams, you should be able to sort of walk through how everything's wired and what component is sort of intended to do what. Then down at the bottom, you've got your component code, you've got your wire color, and then you've got some notes. So we're going to move on to pressure switches. I mentioned pressure switches a little bit earlier, right? So this is the symbol for a pressure switch. On the top switch, you can see that little semicircle, if it were to push up, it would push that switch open, right? So that would be a high pressure switch, and that high pressure switch opens on a rise in pressure. Whereas the diagram on the bottom is a low pressure switch, And as that pressure drops, that switch opens. So you can tell just from looking at the diagram, whether it's a high pressure or a low pressure switch based on which way the switch can open and which way that pressure icon would be able to move, right? Whether it can move up or whether it can move down. It can't go through that circle that indicates your wire connection, right? Or the other side of the switch. Limit switch is the same way, right? That sort of squiggly line tells you that it's temperature, whether it can push up to open on a rise in temp or pull down to open on a drop in temperature is gonna, you're gonna be able to just see that from looking at the diagram. This is a limit switch for a gas furnace. And one thing that I want to point out on these limit switches is on the outside of the switch itself, it lists the temperatures that switch will open at, and then how much it has to cool off before that switch will close. So for this example, that switch is going to open at 150 degrees. So it opens at 150, and then that 20 degrees or 20F next to it indicates that it has to cool off 20 degrees before it'll close again. So from looking at this, we know that switch will open at 150 degrees and that it'll close again at 130 degrees Fahrenheit. Thermostat's the same way, right? It has got switches, and I know this is an old school thermostat, but heat opens on a rise in temp, cooling opens on a drop in temp, right? So when we open that switch, we're not flowing electrons through it anymore. So contactors and or relays. So as I pointed out, and we all know this, the contactor or a relay typically has two different voltages, right? You've got a control side, and then you've got a line voltage side or a low voltage side, right? So up on the top, we're looking at our contacts. This is just like we have in the drawing. This is a single pole contactor, meaning that on the L3, on the L1 to T1 side, there's just a copper bar there. And then we open by interrupting the flow, or we open that switch by opening L3 to T3, and that interrupts our flow of electrons. And the way that we do that is we energize the coil, 24 volts to our contactor coil, which is depicted there in the drawing at the bottom. So what happens when we energize that coil? It creates an electromagnetic field. So it's like an electromagnet. It becomes magnetized, and that magnetic that magnet closes the set of contacts. It actually, the magnet works. There's a spring pushing those contacts up, and then when we energize that coil, that electromagnet or that magnetic field is stronger than the magnet, and it closes our set of contacts. Right, so here's our coil, right? And then, so when we energize the coil, the mechanical linkage that's in there gets pulled closed, and that completes our circuit, right? Closes the switch, completes the circuit, the electrons can move through. If you notice the contacts on this contactor look very similar to the contacts sort of at the bottom right of the screen. We've got two sets. We've got a nice new clean set of contacts, and then we've got some contacts that are pitted or damaged. And so if you have contacts that are not closing completely all the way closed, because you could have some debris in there that's keeping them from closing all the way, you could have sort of insufficient voltage or not enough not strong enough of a magnetic field created by your coil to really pull those contacts all the way. Sometimes you'll hear what's called chattering contacts, meaning that they sort of make a chattering noise because they're not closing and sticking closed like they should. A lot of times that is caused by not having enough voltage at your coil, right? So if you've got chattering contacts, you could have an undersized low voltage wiring. You could have a voltage drop somewhere because you've got a wire nut that's really not very good, or you've got some other sort of voltage drop. We'll talk about that a little bit more here in just a second. So that brings us to the transformer. So a transformer is two isolated coils or two different windings of copper wire wrapped around an iron core. And you've got two sides of a transformer. You've got a primary side, which is your incoming voltage. And then you've got a secondary side, which is your outgoing voltage. Or typically, right, and especially in a residential system, you got a 120 volt, 120 or 240 volt primary, and then you've got a 24 volt secondary. And the current going through your primary coil creates an electromagnetic field, and that magnetism is the electromotive force that causes the electrons to move in the secondary. So that's where our 24 volts comes from our transformer, typically in our indoor piece of equipment. Right? We got our primary, we got our secondary, and that graphic up at the top right, that would be the electrical symbol for a transformer. So just like our light switch or our, the diagram of the condensing unit, our output or our secondary or our side of the transformer also creates a circuit with a power source, a switch, and a load. Those are the three things that are required. If we've got an electrical circuit, we got to have a power source. We got to have some sort of control, and we have to have a load. If we don't have a load and we just hook a wire from the L1 to L2, that's called a direct short. We have to have some sort of load in that circuit. So we're going to move on to troubleshooting, unless there's any questions. Anything we need to stop for real quick?
No, we're good to go, Wade.
Good deal. All right. So in order to do any electrical troubleshooting, you have to have a meter, and you got to have a meter that you can trust. Always keep extra batteries with you, whatever kind of batteries your meter takes. Mine takes 9 volt. I always have a couple of extra 9 volt batteries in my bag. Once your battery starts getting low on your meter, it will give you less than accurate readings, right? Take care of your meter. It'll take care of you. I can't stress that enough. So this is a multimeter, electrical multimeter, and the voltmeter measures the difference in electromotive force between 2 points in a circuit. And we can do that in a couple of different ways. It'll measure voltage drop, and that voltage drop could be because we have too much resistance, or it could be a voltage drop because we are doing some sort of mechanical or electromechanical work, right? When we energize the coil, the energy that it takes to create that electromagnetic field, that extra that the current that creates that electromagnetic field causes a voltage drop. We could also have a voltage drop if we have a wire nut that's not very tight, or we have a contactor that's not closing all the way. The contacts on our contactor aren't closing all the way, and we can have a drop there. And I'll show you a diagram of that in a second. It also will measure the electrical potential. So if we have a switch that's open and we measure on either side of that switch, we're going to measure the electrical potential, not actually the current flow, because there's no current flowing through an open switch, right? We're just going to measure the potential or the electromotive force that's sitting at the end of that switch waiting to be closed so that it can complete its circuit. Typically, your multimeter has an ammeter so that you can measure amperage or current, and that is the clamp up at the top of this this meter that's depicted, and it measures the strength of that magnetic field that's created by the electrons moving through the wire or through the conductor. And then typically it's got an ohm meter, and the to check ohms, the symbol is an omega. And the ohm meter we use to measure ohms or to find the resistance. We can use that to determine if we have an open circuit, if we have a component that has failed or is open, or if we have a direct short. And I'll go through a couple of examples of that here in just a minute. So here we got our meter. It's set to 24 volts. It's set to alternating current. I'm looking at 24 volts. Here's my contactor coil. I've got my closed switch, so I have energized my contactor coil, and I'm measuring on either side of that contactor coil, either side of that coil on my contactor, and I'm reading 24 volts. And so what that means is that I've got 24 volts at my contactor coil, and I'm reading a 24 volt drop across the coil. So that lets me know that my contactor coil is energized. With the switch open and I check there at the contactor coil, I don't have any voltage, right? And it might not be that the switch is open. You might have a broken wire, right? That's a very common repair. You go out, you get a customer complaint is the system's not working, right? So you go out, contactor's not closed, you pull out your meter, you check across the coil, you don't have any voltage, and you start looking for an open circuit somewhere. It doesn't have to be a switch, it could just be a broken wire. So if you check across an open switch, just like I was saying earlier, you're going to read the voltage potential. So if you, and a lot of times people mess this up, especially when they're reading voltages across a thermostat. Reading 24 volts across a switch tells you that that switch is open. If the switch is closed, you should not read any voltage. You shouldn't have voltage drop across a closed switch. It might be very, very minute, but any voltage drop that you have across that switch is telling you that you have resistance there in that switch. And that switch could be a set of contacts. We're going to talk about here in just a second. So here we got a contactor. I'm checking, I got 0 volts in my contactor coil. So my contactor coil is non-energized. I don't have any, it's not creating that magnetic field. I give a call for cooling. I put 24 volts to my contactor. I energize the coil, and now my contact's closed. Right? So you see that red line between L3 and T3. So my contact's closed. If I go down and now I switch my meter leads, and I'm going to check my line voltage. I've got 240 volts from L1 to L3, right? On the line side or the incoming side of my contactor. And then if I check on the bottom or on the load side of my contactor, now I have 235 volts. So why is that? If you detect a voltage drop between the line side and the load side of your contacts, What that tells you is that you have a 5-volt drop through your contactor, through the contacts of your contactor. You'll also see that that will cause an increase in resistance. So anytime you're out doing a maintenance, doing a service call, check and see, do you have any voltage drop across your contacts? Another way that you can read that is by just checking directly across that closed set of contacts, right? And you can see right now that it shows 5 volts AC. So that's the voltage drop that I'm getting. That's what I'm reading, right? Because that switch is closed. It should be reading 0 or very close to 0. If we've got 5 volts voltage drop there, we're gonna see increased resistance every time that set of contacts closes. There's going to be a chance that we arc or start to pit those contacts even more. So that we want to replace this contact. Sometimes you can get a set of contacts that won't close because it has an insect in it, right? Ants love to climb all over contactors, and sometimes they'll get stuck in there. So sometimes you might be reading a voltage drop. The contacts look really good. Everything's nice and clean. Once you clean out whatever debris is in there, insect carcasses or whatever, once you pull out and clean the debris out of there, many times you'll read no drop. So just sort of make that part of your normal maintenance checks. Compressors. So when you are checking a compressor, let's say you replaced a compressor and you're not sure what terminal is what, or you want to make sure that it's wired properly, or any number of reasons. And this is the same for virtually any single phase compressor. So if you don't know what terminal is what, you're gonna switch your meter from volts AC to ohms, and you can see on my meter it's got that little omega symbol, right? So that tells me that I'm measuring ohms or resistance. And then you're just going to measure resistance between all 3 of these compressor terminals, because we got 3 terminals. We've got a common, we've got a start, and we got a run. So we're going to measure between these 2, right? So the upper right and then the upper left and then the right, and between those 2 terminals, we have 1.7 ohms. Then we're going to measure between the next 2, and between those 2 we have 3 ohms, and then between the last ones we have 4.7 ohms. So knowing this, I can determine that the 4.7, or our highest ohm reading or our highest resistance, is going to be between start and run. That's going to be the longest winding. That's going to have the most resistance. So start to run 4.7. So that leads me to determine that the third, or the alternate, is common. If we know that the largest resistance is start to run, then the third has to be common. Well, I know that my next lowest resistance, that 3 ohms, is going to be common to start. So I know that the bottom or the lower terminal on this compressor plug is going to be start, which by default means that the one on the right is run. So common to start plus common to run is going to equal start to run. And it might not be exact, but it's going to be very, very close. If it's not, double check your readings. You don't have to pull the plug off of your compressor to check these readings. You can do it where your compressor plug wires into your contactor and your capacitor, or even on a if it's a 3-phase compressor, they're all going to measure out as the same ohms. But even on like an inverter system, you don't have to pull the plug and get in there to it. The only time I would do that is if I did my compressor check and I didn't like the readings that I got. Let's say I got 1.7, 1.7, and 2. Well, I don't like that. So then I'm going to pull the plug and I'm going to check at those terminals, because I could have an issue with the wiring in my plug or in my compressor harness. So the other compressor check that you can do on the windings is you want to make sure that all of the windings on your compressor, or each one of these terminals, does not have any resistance from each of those terminals to ground. And a ground can be sanding off a nice little clean spot on a refrigerant line. Anything that is a good ground, and your refrigerant lines make a good ground. There's a grounding lug on each one of these units that you can use, but you want to make sure that you get nothing read. It'll read OL, and that is infinite, meaning it doesn't read anything. If you get any sort of a reading, even a 0, that tells you that winding in this compressor is shorted to ground or has a direct short. And so what does that mean? Here's a cutaway drawing of a compressor, and you can see that pink material, sort of pink copperish material, those are your windings for your compressor motor. And what can happen is, for a variety of reasons, right? There could be acid in the system. We could be running the compressor hot. We could be having too much current draw, and that could cause one of the wires or one of the leads in our one of the conductors in our compressor winding to break. And that wire comes loose and it touches the shell of the compressor. So now we have a short to ground. And that's going to trip the breaker, right? So we have a short to ground, it's going to trip the breaker. It should. If this unit is not grounded properly, it should still trip the breaker, but it might not. So in this case, this unit could be electrically charged. So that's why you want to be careful to not just walk up to a piece of equipment and lean against it. So if you walk up to a unit, you're doing a service call, you walk up to a unit, the breaker is tripped, either the breaker on the disconnect, if you have one, if it's a fused disconnect, or the breaker at the panel, if it's tripped, do not reset a trip breaker without pulling out your meter and investigating why this breaker is tripped. It tripped for a reason. It is not a fluke. It is not an accident. Make sure you know why the breaker got tripped. Because what can happen is, let me go back to looking at these pins here. If you have a direct short, what can happen is any one of these pins can vent, or can actually become like a projectile and shoot out of this compressor. It's called a pin ventilation or a compressor vent. And when that happens, the refrigerant that's in that system is going to, it's pressurized, right? It's going to come out of that little hole that was just created. And worst case scenario is when that pin vents out of that compressor, it creates a spark. That spark ignites the refrigerant and or refrigerant oil that's in there and turns that compressor into a flamethrower, which is a really cool tool. I'd love to have a flamethrower. I don't have one, but you don't want to create one on a roof or out beside somebody's house, especially if you're standing right in front of it. So I can't tell you how many times I walked up to a unit in the past. If you've been to any of my classes, I've said this a million times. If there's a wrong way to do it, I've done it. I've reset so many breakers without pulling out my meter. Luckily, I never got hurt, but you can. So just be aware. All right, so transformers. Jumping back to transformer real quick. So a common thing that can happen is somebody decides that the transformer that they have doesn't have enough horsepower, or doesn't have enough juice, or doesn't have enough punch, and I'm going to upgrade the transformer in this unit, right? So again, our incoming power is our primary, our control voltage or our output side is the secondary. And if we look on the data plate or the information on the transformer, you can see your input and your output ratings, right? So this particular transformer has a 30 VA rating, or it has a 30 volt amp rating, or a VA rating is 30. So what that means is that this transformer, and we'll talk about exactly what that means on the next slide. So this is a 30 VA transformer. You could get a 40 VA transformer, you get a 75 VA transformer. You want to make sure that the right transformer, or the transformer that you're using, is right for the application. So our input side of this transformer, happens to be a 120 volt, 60 hertz, 35 watt transformer. But again, our output 30 VA. So if you know the VA rating of the transformer and you know the voltage, you can calculate the maximum amperage load that transformer can handle. So in this example that I've got here, I've got a 75 VA transformer and a 24 volt secondary. Now, is every 24 volt system read 24 volts on your meter? No, but we're going to look at what our ratings are, right? So this output is rated at 24 volts AC, 30 VA, 1.25 amp, and that's where this calculation comes from, right? So 75 VA divided by 24. So a 75 VA transformer that's rated for 24 volts can handle 3.125 amps. So if you've got fuses that are blowing, or if you've got transformers that are having open windings on you, the answer to your question, or the solution to your riddle, is not to upgrade your transformer. Because if you do that, let's say you put in a 100 VA transformer. Well, now it can handle higher amps, but the components that it's powering can't. So you risk killing a board by upgrading a transformer. Right? Say you upgrade the transformer, then you put a 5 amp a fuse in that board, but the board's only rated for 3 amps. Now you're going to kill that board instead of blowing the fuse or killing the transformer. Right. So here's our, and I'm just sort of throwing out broad general terms, right? But 100 VA transformer divided by 24 volts can handle 4.166 amps. So you would not want to put a 5 amp fuse in there. And we hit 9 o'clock. So before we move on to the, let's do the quiz questions. Oh, all right. So everybody go ahead and open up the chat window. We got, get ready to answer. We got the first of 4 quiz questions. And the first one is, what is electromotive force? Movement of electrons. Yep. It is the force that causes those electrons to move. Which type of wiring diagram shows component location and specifies wiring color? A complete circuit must contain a power source, a control, and a what? Nice. Got to have a load.
We got a
How
couple
many volts would you expect to read across a closed switch? Closed switch. How many volts are we going to read across a closed switch? Zero. If you're reading any voltage across your closed switch, you got a problem. You're dropping volts. You got too much resistance across that switch.
There was
And
one question that was asked. Did you see it, Todd, before everyone
Yeah.
started commenting?
yeah,
Okay.
they're just asking what's the best way to troubleshoot a blown 3-amp fuse.
Well,
It kind of depends on the circuit, the blown 3-amp. I'm assuming he's talking about the fuse in the air handler, the typical
right.
fuse in the air
Yeah.
handler.
So a lot of times what I do when I find a blown fuse in something, if you have one of those poppets, that can be really helpful, right? A 3-amp poppet where it's resettable, you can put it in there and start troubleshooting. A lot of times the best way to do it is just to start tracing your wires. I know that sounds tedious, but if you've got a blown fuse, a lot of times you're going to find something at your outdoor unit, right? A rodent or critter chewed on a wire, weed eater hit a 2-wire or a wire going outside, whether it's a heat pump or a condensing unit. But sometimes you just got to start looking. The easiest way is to trace your wires, or else you're going to go through a lot of fuses. You ever walk up to a unit and you see like 20 or 30 fuses laying around, you know that somebody had a tough time troubleshooting a low voltage short. And if you don't have a toolbox full of fuses, the best way to do it is just to trace every wire. Anything else?
No, I think that does it.
Okay, awesome. Well, thanks for your time, everybody that attended. Thanks, Todd and Nicole, and everybody at Tropic. I appreciate your time.